Welcome to Electronics with Emrys. This is the first episode of Schematic Upgrade, a new series where we will explore vintage circuits and update them with modern tech wherever we can. The book I'm looking at today is the Master Handbook of 1001 Practical Electronic Circuits, edited by Kendall Webster Sessions, circa 1975. What better way to kick off Schematic Upgrade than with the book's first circuit, a reverse polarity protection design. It's actually two circuits, and we'll tackle both in this episode. These are both protection circuits so that you don't mess up your electronics whenever you connect a supply backwards. The first one just adds a diode to block current whenever your battery is connected backwards. And the other one corrects the polarity so that if you connect something backwards, it will still be connected forwards to your supply. Let's take a look at these in a simulator. Before we start adding protection circuits to see how they behave, let's check how this circuit behaves with a normal connection and no protection circuit. So I have a load here of a 1 kilo ohm resistor and a reverse biased 1N4148 diode. It may seem like a strange combination, but it's actually pretty common to have a circuit that's going to be drawing a relatively constant current, and then it'll have a bunch of diodes in there as part of the ICs, and if you reverse your supply, you'll see a lot of current flow through those. Running my simulation, I can see that there's only nanoamps driving reverse through this diode, and I've got 9 milliamps going through the 1K resistor, as you'd expect. Now with our supply reversed, we'll see that we're still getting 9 milliamps through the 1K resistor, although now it's going the other direction. But our diode is now conducting and we have 13.5 amps of current, which probably melted this circuit in the real world. So we definitely need some sort of protection circuit. Now the one that the book showed us was just using a diode in series. So let's go ahead and place that diode directly in series with the supply, and we'll see if that works. Running the simulation, we've got 8.2 milliamps, so we're not quite getting 9 volts over here. Now we've lost about 0.75 volts, but we are getting current flowing through our 1K resistor, and we've got a few nanoamps going through the diode over here. If we reverse our supply, then we see that there is no current flowing. So we're only getting 9 nanoamps here and femtoamps through the diode. So basically this diode is doing its job, it's just blocking any reverse current. So that definitely works to protect our circuit. The most obvious upgrade to me is to change out the silicon diode for a Schottky diode. So now this will have a lower voltage drop on it. Running the simulation again, we see that we're getting about 8.8 milliamps because we've got 8.8 volts across this resistor. So we're getting more of our 9 volts over to our load. And we've got some nanoamps going through that diode just like before. Now let's try reversing this. With the supply reversed, you'll see that we get a lot more current than we did before going through the diodes. Now this is 171 microamps, which is significantly more than what we had through our other diode, but it's still not very much current and nothing would be damaged from this. 131 nanoamps going through the diode over here, and our resistor is where most of that current is flowing through. Now this is what I would consider to be one of the best protection schemes, at least today. We're using an N-channel MOSFET to prevent current from flowing whenever our input voltage is reversed. So first we'll start with the voltage going the way it's supposed to. We get 8.99 milliamps going through the resistor and nanoamps going through our diode, exactly as we'd expect. The MOSFET has very little resistance whenever it's biased on like this. After reversing the supply, we can see that the current through the resistor is down to picoamps, and the diode is the same, femtoamps. So basically there's no current flowing through this circuit at all. So our MOSFET here has cut off the ground return line because the supply is backwards here. You can actually do the same thing with a P-channel FET. I don't usually do this because I have more N-channel FETs on hand than I do P-channel FETs, but this works just fine. Running the simulation, you can see that my resistor gets about 9 milliamps going through it and no current flowing backwards through this diode right now. Reversing our supply, we can run the simulation again, and we see that there is very little current flowing through the resistor or the diode. So this has successfully cut this off. Now, something that is almost never done, as far as I know, is to use both a P-channel and an N-channel FET. This is not something that's really necessary to do for any reason, but you could definitely do it. Running our simulation, we can see that we're getting 8.99 milliamps going through our resistor, just like we'd expect with just one of these. But with both, we get a little bit of extra resistance because we now have two transistors in the way of our supply instead of only one. Reversing this, we get the same result with very little current flowing through the circuit over here, so this protects the circuit just fine. It's just a little bit weird. The way I've drawn this is a little bit strange, but this is a full wave rectifier. Running our simulation, we can see that we're getting about 7.5 volts across that 1K resistor because we're getting 7.5 milliamps through it. And if we reverse our supply over here, we're still getting 7.5 milliamps in the same direction. Even with the supply reversed, we're still getting the same polarity on our load over here. And that's because the positive end of this is connecting to this diode, which is connecting to the positive end of our load. And the negative end of our supply is connected to the negative end of this diode, which connects up to the negative end of our load. So basically, our current is able to flow through the load and then back out this way. Whenever we have it flipped around this side, it's going to go through this diode, through the load, and then back through this diode. So you can see why I drew it this way, because this is a very clear and easy to understand loop. And then whenever you reverse this, the loop just goes back the other way through these diodes, basically. Now, this isn't a very practical circuit because you lose a pretty good amount of voltage to the diode bridge here. You could change these diodes out to Schottky diodes, and that would make things a little better. I went ahead and swapped out my diodes for Schottky diodes, so now our load is seeing about 8.6 volts across it, which is definitely significantly better than what we were seeing with the silicon diodes. And of course, if we reverse our supply, we're still going to see 8.6 volts over here because there's no real difference how you connect this. So if I was going to use a circuit like this, I would probably use this approach because it's going to give you the best of both worlds here. Now, there is another approach we could take, and that would be to use MOSFETs instead of diodes here. And I'm not going to go through all the different steps to do this, but I'm just going to show you my design. I know this may look a little bit strange. I've set up two P-channel FETs at the top and two N-channel FETs at the bottom. And essentially this is a MOSFET full wave bridge rectifier. So the idea here is that I've set up the same type of protection circuit that I showed you earlier that I said was very impractical. This one is still kind of impractical, but it's a little bit better because now we're able to have a polarity agnostic input for our battery over here, and we're not going to lose very much voltage because we're using a MOSFET bridge instead of diode bridges. Running the simulation, I see I'm getting 8.99 milliamps through this. So I'm getting 8.99 volts through to the other side of the bridge here. Reversing the supply and running the simulation again, I see that I still get the same polarity and 8.99 milliamps. So this is a great way to be able to connect up a battery without having to worry about the polarity at all. I'm not really sure how practical this circuit is, but it seems to work significantly better than the full wave rectifier does whenever it comes to reversing a supply and having a load that still gets connected up the right way around. So that's a wrap for our first episode of Schematic Upgrade. If you have any vintage circuits that you want to point me towards, please put them down in the comments, and I'll take a look, see if I can include them in a future video. If you made it to the end of this video, I want to say thank you very much for watching, and I hope you have a great day.